Hi everyone. In the previous video, we started with Newton's second law, and we turned that into Euler's first. And of course, we saw that these two equations were equivalent. The first one was for particles, the second was for bodies with volume. And we introduced a concept to go along with these, which was linear momentum. Well, what we're going to do in today's video, we're going to derive Euler's second law. And the concept to go with this one is angular momentum. Now, what this is going to look like. Recall Newton's second law, Euler's first. We said that the sum of forces on some object, let's say object A, this was equal to ddt of this quantity linear momentum, so ddt of Ka. What we're going to derive today, Euler's second, is going to look like this. The sum of moments on body A taken about point A. Now, recall that when you're doing moments, it's the forces acting at a certain point create the moment, and then you are taking the moment about some other point. And this is going to equal this new quantity, angular momentum, which is h. And since we're doing moments on A about A, this is the angular momentum of body A taken about point A. All right, so what we're going to do is we're going to start with Newton's second law, Euler's first, and we're going to ask the question, what happens to the location of the forces? So let's clean this up and let's get started. We have a general body A with known center of mass A, and we have broken this body into infinitely many differential bits of mass. I've drawn two different forces acting on body A. One of them is at point B sub I, and then another force, which is same magnitude, same direction, is acting at some other point. We know that if we were going to sum the forces on A, these two forces would be equivalent. However, because they're at different points, they create different moments about point A. And what we want to do is we want to consider how those locations of the forces affect the motion of body A as a whole. So let's start by writing Newton's second law for this little differential bit of mass. So the sum of forces on body B sub I, we know that this is equal to ddt of mbi vbi. We want to look at the moments. So let's consider the moment of the forces acting at point B sub I around point A. Now, how are we going to get this? Well, you might recall from a physics class that moments are R cross F. If you need a refresher, let's say that you have a point A and point B, and there is a force acting at point B. Let's call this L in the positive x hat in direction, and then this one is in the positive y. So the moment generated by this force at point B, the moment about point A, so this is going to be the moment of the force at B about point A. This is equal to the position vector from A to B. We want to be very specific in the direction of these position vectors, because if you get it wrong, the sign of the moment changes. So this is P, A to B, cross the sum of forces acting at B. So what is this? This is going to be L in the x hat in direction, cross F in the y hat in direction. And we know our cross product rules. X cross y is positive z, and then we multiply the scalars, F times L. So from inspection, this force generates a positive moment, and there's the positive moment being created. So in this example up top, we need to do the position vector from the point where the moments are taken about to the point where the forces are acting. So the position vector from A to B, and this is cross the sum of forces on B sub I. Now, if we're going to do cross product to the left, we can do cross product to the right as well. sum of moments on BI about A. This is equal to P ABI cross MBI VBI. Oh, left out the DDT. Cross DDT. There we go. MBI VBI. All right. We want all of the moments acting on body A. We want the sum of moments on A about point A. Well, that means we just need to add them all up. So we're going to do the infinite summation on all of these sum of moments B sub I is about A, which means we're going to do an infinite summation on the right-hand side as well. So infinite summation of P ABI cross DDT of MBI VBI. All right. Now, the left-hand side is starting to look good. Remember, the goal of this is that we started with Newton's second law, which is just translation, and now we want to consider rotation. So we have sum of forces, we have their rotational equivalent, sum of moments. The right-hand side here is the change in linear momentum. We want the right-hand side of this to equal change in angular momentum. Now, when we look at what we've derived, we have an infinite summation and we have a DDT. What we would really like is to have the DDT outside. Right now, however, the DDT is inside. So we have to work with this, right? We have to work with the right-hand side of the equation, and we have to find some way to get the DDT to the outside of this equation. So here's what we're going to do. Let's just pause on this term for a moment, and let's consider, what if we did this? What if we did DDT of the infinite summation of PAVI cross MBI VBI? Well, if we're taking DDT of this term, we need to do a product rule expansion. So this is going to equal DDT of the first term. So let's say I can move the DDT inside for these. So let's put the infinite summation on the outside. DDT of P ABI cross MBI VBI plus the next infinite summation, and this is now P ABI cross DDT of MBI VBI. We could further expand this term, right? We could do a product rule expansion where it's DDT of MBI, DDT of VBI, etc. However, we can see that this is now equivalent to this. We can put some brackets on it to make it a little more clear. Okay. So what happens to this first term? If we can prove that this first term goes to 0, then we can say that the top, right, this term is equal to this term, which means we can take this and we can substitute it into this equation such that this on the top is equal to sum of moments on A about A. Well, there's two ways this can go. We can look at this and we can consider that we're looking at a rigid body. And if it is a rigid body, then the body itself does not deform. So the position vector from A to B is constant. Now, what if it's not a rigid body, or what if we're taking this derivative with respect to an inertial frame? For example, DDT of PABI. I'm just going to put it. I'm going to put it down here. DDT of PABI is going to equal V ABI, the relative velocity from point A to point B sub I. And consider that this body could be rotating, right? So there's like a proof within a proof. If we can prove that this term, this DDT of PABI, If we can prove that this whole thing is equal to 0, well, that's going to take care of this for us, right? We could look at this rigid body assumption and you could say, well, the body doesn't deform, so we're just going to set it equal to 0. Okay, but consider that this part still stands, right? You can't just drop this and say that it's equal to 0. So what I'm going to do is I'm going to erase all of this, and what we need to do is we need to prove that just this term if we can prove that this term is equal to 0, then that means that let's say that this was term number 1, and this one is term number 2, and we can call this one as term number 3. If term 3 is equal to 0, then term 2 is equal to term 1. Right? This is also term 1, and then we could take term 2 and we can plug it directly into this equation and set it equal to sum of moments on A about A. So the goal now is just to show that term 3 is equal to 0. So let me clean this up, and we're just going to prove this. It's going to take a little bit, and once we prove this, then we're going to immediately take 2 and we're going to plug it in right here. So let's do that. Here's the proof that we need to do. I've written the expression here, and I've set it equal to 0 because, again, we need to prove that this is equal to 0. So how are we going to approach this? Let's start by focusing in on the PABI, and let's do a little kinematics. The position vector from n to b sub I we can write as p into a plus p a to b sub I, right? We can take this and we can solve for the PABI. And this is going to equal P in BI minus P into A. So let's take this and let's put it into this expression. So 0 is going to equal infinite summation of ddt of this P in BI minus P in A. And then this is cross in BI VBI. Okay, what we're going to do is let's distribute the ddt to each of these, and we can break it into 2 different expressions. Now, ddt of P into BI, this is VBI, and ddt of P in A, this is VA. So 0 equals the infinite summation of VBI cross MBI VBI minus the infinite summation of VA cross MBI VBI. All right, what are we going to do here? Well, the MBI, this is just a scalar. We could move this thing throughout this expression. But this says that this is VBI cross VBI with the scalar, right? Just pull the scalar to the front or the back, wherever you like. A vector cross itself is equal to 0. So this first term is equal to 0. So now we just have to focus in on this term. So let me clean up a bit. And we need to say that 0 equals, here's our infinite summation. This is VA cross MBI. Now, and I did drop the 0 because it doesn't matter. What are we going to do with the VBI? Consider that VBI, we know that this is ddt of P into BI, which is ddt of P into A plus P A to B sub I. We just did that a minute ago, right? And if we evaluate this, well, ddt of P into A, that's just VA. And then the second piece, we can actually represent that with transport theorem. We can do omega into A cross the position vector from A to B sub I. So let's take this expression now and let's replace the VBI with it up here. So this is VA plus omega NA cross PA to B sub I. All right, so how does this help us? There's a plus here, which means we can break this into two different expressions. Let's do that. 0 equals, here's our infinite summation. This is VA cross MBI VA plus. Here's the second term, infinite summation VA cross MBI PA, let's say omega NA cross PABI. There we go. All right. What's going to happen on the first term? Well, we've got the scalar MBI again, right? We can move that anywhere we want. And this says VA cross VA. So this term is also now equal to 0. So we just have to deal with this last term. What are we going to do here? Well, we're going to do two things. First of all, again, MBI is a scalar. We can move it anywhere we want in this expression. Next, what is constant in this with respect to the summation? Consider that VA has nothing to do with the index I, and neither does omega NA. So we can take the VA cross omega NA, and we can extract it out of this infinite summation. So our proof now, 0 equals VA cross omega NA cross, and I'm going to write it as infinite summation. I'm going to bring that scalar in B sub I multiplied by P A to B sub I. Now, in the previous video, when we talked for a bit about center of mass, we showed that this expression, this is equal to 0. So we had to do a little bit of work, but we were able to prove that this expression on top is equal to 0. And if you recall, the whole point of doing this proof was that we're going to relate it back to that original derivation. Because this is equal to 0, we can now say that the sum of moments on body A about point A, this is equal to d dt of infinite summation of the position vector from A to BI cross MBI VBI. That was the point of all of this. Now, again, also, I'm going to write Newton's second law, Euler's first. The sum of forces on A, this is equal to ddt of Ka. All right. So here's what's going to happen. We're going to call this the angular momentum. This is h of A about A. Now the letters here, again, this is different from when we're doing position vectors. This is different from when we're doing moments, with and of course different from when you're doing forces and linear momentum. With the moments, we're saying that the angular momentum of body A about point A, right? And that's consistent with the angular momentum. This is the angular momentum of body A taken about point A, so about its own center of mass. So we can simplify this. We can write it a little cleaner anyway. We can say that the sum of moments on A about A is equal to ddt of h A about A, where h, the angular momentum of A about A, is this. Now, that looks cleaner, but what are we supposed to do with this, right? This seems like a very nasty expression. What we're going to do is I'm going to clean this up, and we're going to focus in, again, just on this part inside of the ddt, and we're going to see if we can come up with a more useful way of representing this whole thing. Okay, so let's do that next. So here's the angular momentum. I've rewritten it. We want to express this in some cleaner, easier way that we can actually use. So what can we do with this? Well, we've done this before. We've gone in and we've kind of massaged or manipulated these equations a little bit. So we can express this VBI using transport theorem. I'm just going to say equals, right, because we're going to have to write this numerous times. So this is equal to infinite summation P ABI cross MBI, and here comes the transport theorem. This is VA plus omega NA cross PABI. And let's break this into two terms. So here's the first one, infinite summation PABI cross MBI VA, and plus infinite summation PABI cross MBI omega NA cross PABI. All right. So what are we going to do? Let's focus on the first one and consider, we can move this around just a little bit. The MBI is of course the scalar, and we can shift that as we need to. Okay. And one thing we can do is notice that the VA is also a constant with respect to this summation. So let's, I can't pull it out of the summation to the left, but let's isolate it to the right. So let's rewrite this first term, and let's write it as MBI PABI. I'm going to put some brackets around that. And then that term, this is a vector, this vector cross VA plus, and we'll get to that part in a second. So what is this? We've seen this one crop up now several times. This came from definition of center of mass. And as we have said, and as we have used in the previous parts of this derivation, this is equal to 0. All right, so what does that leave over here? Well, there's a series of cross products, and PABI, if we were able to express PABI cross PABI, then that would be equal to 0 as well, right? Because a vector cross itself is equal to 0. Unfortunately, there's this omega NA right in the middle, right? And omega NA, it is constant with respect to the summation, but there's no way to extract this omega NA to pull it out by itself. So what we're looking at here, this term is what is called a vector triple product. So this is going to be our vector triple product. So there are some nice identities that come from our friends in the math department that we can use to manipulate this term to do some rearranging. So let's do just a little bit of cleanup here. And I'm going to leave these on the board for just a moment so that we can have them, we can look at them. So first of all, let's talk about the vector triple product. If you have A cross B cross C, we can rewrite this. I'm going to read from my notes because I absolutely do not memorize these. So this is A dot C, so dot product. Vector dot, a vector is going to yield a scalar, and it's that scalar multiplied by the vector B, and then this is that first piece minus A dot B multiplied by C. So how does that apply to this particular part? Well, the PAB, this is our A, and the omega NA is B, and the PAB is C. And then, of course, the MBI is a scalar. So we can actually bring the scalar all the way to the front, and we can rewrite this term, because this is all that's left over. We can rewrite this according to this vector triple product identity. And when you do, this is what you get. HAA, angular momentum of A about A, this is equal to, we still have this infinite summation. I'm going to put the mass first, and then When you apply that vector triple product to this expression, here's what we're going to get. So we're going to have PABI dot PABI. This is going to yield a scalar term, and it's this multiplied by omega in A, and then plus, sorry, this one's minus. This is now PABI dot omega in A, and then multiplied by PABI. Okay. Now, we do know from dot products, if you have a unit vector and you dot it with a unit vector, you'll get 1. However, if you have directions, right? Like we've done dot product several times when we were doing constraints. We would say x hat dot x hat equals 1, right? But that's not what happens when you have these position vectors. And we don't know anything about these position vectors. We don't know their magnitude. Maybe they're in one direction only. Maybe they're fully populated in all 3 dimensions. We're doing this fully general, so we cannot just say that this is equal to 1. So here's what's going to happen at this point in the derivation moving forward. There's no more cancellations, and there's no more manipulation of the equation to get something easier. What we have to do at this point is we just have to make some assumptions about the position vectors and the angular velocity, and let's just see if we can find an easier way to express it. Let's say this position vector, PABI, is some distance x in the x hat a direction, and this is x sub I. So x sub I in the x hat a plus y sub I in the y hat a plus z sub I in the z hat a. Now, a quick comment, note that we're doing body frame, right? Because your body, your rigid body could be rotating, and we want to define the geometry of this body in its own body frame, such that this position vector is constant. If we were defining this in the inertial frame, then these specific dimensions would be changing, right, every time this body undergoes some kind of rotation. So this is explicitly in the body's own frame. And next, let's make a similar assumption about omega in A. We're not going to do a simple rotation this time. Let's say that this body is undergoing some general rotation. So it is possible that this body is rotating in 3 dimensions. So we're going to say that there is some angular velocity in the x hat a around the x hat a axis, some angular velocity around the y hat a, and some angular velocity around the z hat a. All right, so this is fully generalized. What we're going to do next is let's take these 2 vectors and plug them in, and let's talk about what you get when you do that. So I'm going to give it to you as kind of the first level. If you take these and you just put them in and you calculate these dot products and multiplications, here's what happens. We still have this infinite summation. We're going to bring down the mass. Okay, so when you perform this dot product, you're going to get x sub I squared plus y sub I squared plus z sub I squared. And take note that this is a scalar, and then we're just going to multiply by omega in A. So omega x, x hat a, plus omega y, y hat a, plus omega z, z hat a. All right, there's the first term. The second term, performing the dot product and then that multiplication, here's what we get. So minus xi omega x plus yi omega y plus zi omega z. And then we're going to multiply that by the position vector. So that position vector was x sub I, x hat a, plus y sub I, y hat a, and z sub I, z hat a. Okay, close the brackets. So here's that first level, right? We just took the position vector and omega, we put them in, and then we expand. Here's what we get. Now, what you would do is you would take this term and you would distribute. You would take this term and you would distribute. And clearly you're going to get something very big and very nasty. What we can do though is we can collect terms, and we're going to collect terms according to the directions. So let's make one expression on top for everything in the x hat a, another expression in the y hat a, another expression in the z hat a. All right. So the angular momentum of A about A, here we go. Infinite summation, MBI. And I tell you what, let's actually, just to keep it real clean, I'm going to open the square brackets here, and then I'm going to lay out the 3 rows right on top of each other. So here's the first terms. Xi, whoop, already messed up, yi squared plus zi squared, and that's multiplied by omega x minus xi yi omega y minus xi zi omega z. All right, and all of this is in the x hat a direction. Plus, this first one is going to be minus xi yi omega y plus xi squared plus zi squared omega y. Sorry, this one's omega x, yeah. And minus yi zi omega z, yeah, and that's in our YA direction. And here's the third row, plus this is negative xi y z I omega x. Next one is minus, this is yi zi omega y, and plus xi squared plus yi squared times omega z. Then let's close. That one's in the z hat a direction, and then close the brackets. Okay. So this is that full expansion, and we've arranged it according to directions. Now, before we move forward, think about the dimensions of this term. We have some quantity, and it's scalar, some scalar quantity in the x hat a direction. We have another scalar quantity in the y hat a direction, another scalar quantity in the z hat a direction. So that means that this quantity HAA, this is 3 by 1. It's a 3 by 1 vector. And you take all of these things, you multiply by MBI, and you perform this infinite summation. Again, we still need some better way to represent this. So what we can actually do, I'm going to put it up in this corner, but consider it's not actually inside of this expansion. I'm just putting it in the corner out of convenience. If you have an object that is 3 by 1, let's say that we do some linear multiplication, A times B equals C. And C is a 3 by 1, and B is a 3 by 1. We can achieve this if A is 3 by 3. So we can, if we can find some way to represent all of this, so if all of this as we have it right now is C, and if we can deconstruct it and represent it as some form of A times B, that seems a little easier. So what we're going to do is we're going to let the geometry, right, because these are the geometric terms, the x sub I and z sub I, we're going to let the geometry fit into this A matrix. And the A is also going to contain this, this scalar mass. And then notice that the B could actually be your angular velocity, right? Because look at how the angular velocity terms have been distributed. So what we're about to do, this is actually where definition of inertia comes from. Consider that if you have a differential bit of mass it has a particular place in the geometry of the object, right? So we're taking the position, and here's the scalar mass associated with that point. So what we're literally looking at is the distribution of mass in the geometry of the object itself. So here's how we're going to clean this whole thing up. First of all, we're going to represent the geometry of the object, the distribution of mass in the geometry, with a matrix called I. Now, if you've taken linear algebra classes, I in linear algebra can mean identity. So for example, 1, 1, 1, and all of these are zeros. That is not what we're doing right now. So when I write this I and with the subscripts, it is not an identity matrix. Instead, this is inertia. And inertia, you can think of it as a matrix. More formally, it is a dyadic. And then it's going to be I dot product with omega in A. So let's lay it out. Big picture. Here it is. Xi squared, man, did it again. Yi squared plus Zi squared minus Xi Yi minus, Xi Zi, there we go. Minus, this is Xi Yi plus, well, this is Xi squared plus Zi squared, and then this term over here is going to be Yi Zi. The one on bottom, this is Xi Zi. Here we have Yi Zi, and here is Xi squared plus Yi squared. Okay, there we go. Now, all of these terms are actually multiplied by the MBI. So let me make a little bit more room over here because I left the infinite summation out. Infinite summation, MBI, this is equal to HAA. So here's the first term in the angular momentum. This infinite summation, MBI of all these little bits, that is going to make this inertia dyadic. And then we are dotting this with the angular velocity vector, which is W omega X, omega Y, omega Z. Now, if you think about the directions of all of these, of course, this one was XA, YA, ZA, and this dyadic, your bases are XA, YA, ZA for the rows, and also XA, YA, ZA for the columns. If you really dig into this, for example, this top left term, we would write it as Yi squared plus Zi squared XA, XA. And then when you take it and you dot it with X hat A, you lose one of these X hat A. So for example, if we take this, and if we take this and we dot it with X hat A, these, the outer X hat A and this X hat A, these equal 1, and what you're left with is the Yi squared plus Zi squared in the X hat A direction. Now, when you dot it specifically with the angular velocity, you're going to have this term multiplied by omega in A. All right. So you might be looking at this and just wondering, what the hell, right? Here's what all of this means. Here's what the implications of all this mean. Now, we can't literally perform this infinite summation, but what we can do is we can replace the infinite summation with a continuous description, which would be integration. So we'll do that in a different video where I'll show how to actually solve for these specific terms from integration over the volume of the object. But for now, what we would do with this is, if for an actual object, if you're doing something in, well, if you're doing theoretical shapes, like if you're doing generalized spheres and cylinders, things like that, this inertia dyadic actually, again, you get it from integration, but you can just look these up in tables. They're usually on the inside covers of your textbooks, or you can get them off of Wikipedia, honestly. If you've seen any numbers for objects like 1 over 12 ml squared for cylindrical rods, for example, what this term literally is, it's this. It's some of these diagonal terms, okay? And these will come from, for simplified shapes, they'll come from integration. What if you have an actual real world part, right? If you're designing something and you need this inertia dyadic, well, you're probably going to design it in a CAD software, SolidWorks, Pro Engineer, something like that. And what the program will do is it will take your part and it will discretize it, right? It'll apply a mesh to your part, right? It'll break it into all of these different little sub bits using nodes, and it will literally perform a numerical summation on all of these little differential parts. So the higher resolution mesh you use, the more accurate answer you will get for this inertia dyadic. And in modern day software, it's literally just a button that you press inside of the software, and the software comes back, assuming that, I mean, it's going to know the geometry, you tell it the material it's made of, and it'll come back and it'll tell you, hey, the mass of the object is its center of mass is located at this point, and its inertia dyadic is this, and it'll just spit the numbers out. Okay, for a rigid body, this matrix is constant. This dyadic is constant. So unless you're doing something with rockets, right? Both the mass and the distribution of mass within the object itself is constant. Now, when we write it, we usually don't do all these x sub I plus z sub i's. Let me show you a little better way to write this. Okay, so we're still looking at this quantity, HAA, the angular momentum of A about A, and we're still looking at this inertia dyadic. Now, take note that I'm writing it with a dot product, but consider this is, the dimensions of this are 3 by 3, and the dimensions of this one are 3 by 1. So if you've taken classes in linear algebra, you know that you can just perform matrix vector multiplication, and it's equivalent to doing the dot product in this case. Now, the way that we usually write these inertia dyadics is like this. The term in the top left corner, this is IXX. The term in the middle is IYY, and the bottom right is IZZ. These have a name. These are called moments of inertia. And some interesting properties is that they're always positive. Because if we go back and we looked at the equation for it, the equation for IXX, I'm going to get it right this time, is yi squared plus zi squared multiplied by mbi. Well, the mass is constant, and regardless of where in the geometry of the object, it doesn't matter if y is negative or z is negative, we're squaring them. So these moments of inertia terms, these are always positive. Now, the off-diagonal terms, for example, this one is IXY, and we could write this one as IYX. These are actually the same. These two will have the same value, because if you go back and you look at the equations, this one was negative xi times yi times mbi, and this one is negative xi times yi times mbi. So these terms can be positive or negative, depending on, first of all, it's got a negative sign on it, but depending on if x is positive or negative, or if y is positive or negative. So when you generate these inertia matrices, you'll always see positive values on the diagonal, and you might see negative values on the off-diagonal terms, and that's perfectly normal. So that's one characteristic, and then the other characteristic is this symmetry across the diagonal. So top right corner is IXZ, bottom left is IZX. These are the same. And then IYZ and IZY. These are the same as well. So when you're working problems, if the problem asks for find the angular momentum of this body about its own center of mass, what do you need to do? Well, you need to write down what it is. The angular momentum of A about A is the inertia of A about A times omega into A. If you're looking at body B, you write down the angular momentum of B about B. This is the inertia of B about B times the angular velocity from N to B. Now, it doesn't matter how you set up your frames or how you define your rotations. This is always the absolute angular velocity from the end frame to the body frame for this body. What do we do next? Well, next, if you need a numerical answer to the problem, you go to your textbook or to an online source or to your CAD software, and you get this matrix, this dyadic, and you take it, the numbers, and if it's, let's say that you're doing some theoretical cylinder, right, and it's the 1/12 ml squared. Well, this becomes a number then, right, because you know the mass of it and you know the length of that cylinder, right? And then you just have your angular velocity vector and you multiply these two things together, and that is literally the answer. Okay. I do want to make a couple of final comments before we move on. And this next bit is actually critically important, so please don't skip it. Recall the whole point of this was to write the sum of moments on an object. We're doing A about A. This is equal to ddt of now this quantity that we know what it is, h of A about A. And let's bring in the definition. So this is ddt of IAA omega in A. Okay. So what happens when we take the derivative of that? What's going to happen? Well, we're going to treat body A as a rigid body, which means the mass doesn't change, it doesn't undergo any deformation, which means the inertia doesn't change either. So we can do a product rule expansion on this if we want. We could get a ddt of the IAA term, that's going to be 0. So sum of moments on A about A is equal to, the first product rule term is 0, so we're just going to leave that one out, times omega in A dot. Now, just hold on a minute. Recall that this was specifically in body frame. So I'm going to come over here and I'm going to write A frame. So what does that mean? We're taking the derivative of some quantity that is in a moving frame. That means we have to do transport theorem. So we're not done. The answer also has this attached. Now you might think, oh, well, omega in A cross omega in A, that's a vector cross itself, that must be 0. Realize that there's this inertia matrix, this dyadic in the middle. Now, if you're dealing with some simplified systems, if your inertia matrix just happens to be identity, for example, there are some cases where this does end up equaling 0. But in general, no. If you're dealing with spheres, for example, consider that your inertia matrix, the mass is equally distributed. It doesn't have to be exactly identity. It could be identity multiplied by a scalar. You could have an inertia matrix that looks like 2, 2, 2, and these are all zeros. Well, that's just identity, a 3 by 3 identity multiplied by 2, right? So in that case, the 2 comes to the front. The identity in between just yields omega na, so it's omega na cross omega na. There are some times where this additional term goes to 0, but for all real-world objects, it doesn't. And you can get a lot of interesting behavior out of this additional term. One thing, for example, we're going to do this in another video, and I'll actually show a little bit of simulation to back it up. But if you have an object that is asymmetric, this object, when it starts spinning in space, can actually undergo some tumbling effects. And I'll show you some examples of that, both real-world examples and also backed up with simulation. So this, as we have written it, this is now the solution. This is the real Euler's second law. So this is Euler's second. Okay, so where do we go from here? First of all, you can do your homework now, which is great. So make sure you're comfortable doing, or at least being able to write Euler's second and Euler's first, Newton's second, so sum of forces on A. Now ddt of the linear momentum is going to yield mass times acceleration. Again, this is not true for things that are changing mass, but we'll do that. We'll have that talk in another video. So here's Euler's second. Here is, I'll write this as Euler's first. And usually we call this Newton's second. These two equations together, this is the Newton-Euler equations of motion. And this is really what we're building up to this semester. We need to be able to do the kinematics, which define the linear and angular accelerations. We have gone through now, we've talked a bit about mass and inertia. You know what this inertia dyadic is. And of course, after later in the semester, when we get past the next round of exams, we're going to talk about forces and moments. So then we can build these whole equations, and then we can solve them. We do have a couple other topics we have to talk about before then. For example, what if we took the moments about a different point? In this case, we took all the moments about point A. There are times where it perhaps is more convenient to, instead of taking your moments about the center of mass, what if instead you took them about another point? What if we wanted to take the moments about this pin joint, for example? Then we have to go back and we have to modify Euler's second law to find the inertia, not about point A, but we have to find the inertia of A about a different point. So that's going to be another video. And now that we have this understanding of mass and inertia, we can also talk about energy quantities. So we'll do another video also where we derive kinetic energy and potential energy from work. So just be aware we've got those coming, but that is it for this one. I will do another video where we do a worked example, where we talk about how to actually find, we could do this pendulum, we could do a mechanism. What would be the linear momentum and what would be the angular momentum for this series of bodies. Okay, so that's it for now. Best of luck. I'll see you around.